All right, let's take a look at our last two models of the atom. We've already been talking about the fact that from looking at the line spectrum for hydrogen that we can note that there are always certain colors that hydrogen releases when it is excited by either an electric current or by a flame. And the ideas of Bohr were that the reason for those unique patterns always being emitted from hydrogen and other elements is that electrons are confined to energy levels. And the idea of a quantum of energy or a fixed or finite amount of energy came from Max Planck or Planck, and Bohr was basically applying his idea to why this line spectrum could always be observed from every element and always be unique. And so Bohr hypothesized that electrons can only have fixed amounts of energy. With fixed amounts of energy, the electrons are then orbiting the nucleus at fixed distances or fixed energies, like the planets orbit the sun. So the problem that we had when we talked about Rutherford's model is that we have the teeny tiny positive nucleus where the majority of the mass of the atom is. There's all this empty space, and then there's electrons somewhere outside the nucleus. And the problem was, why don't the electrons just run into the nucleus? They are oppositely charged. They should be attracted. And so Bohr, although not quite explaining why the electrons are in these energy levels, was saying that electrons must be in these energy levels because we can always see these patterns of colored lines. That means that the electrons are jumping from one level to another. But the difference between those energy levels in terms of the amounts of energy that they're changing, the electrons are changing by, is always the same. And so we always see the same pattern of colored light. We're going to call this the planetary model. And again, electrons, like the planets, orbit the sun in fixed paths. We can picture the electrons orbiting the nucleus in the same fashion, except, again, they're orbiting at fixed distances because they have a fixed energy. And so that amount of energy is what keeps them from slamming into the nucleus. Just like if you were holding yourself away from something that you're attracted to or being pulled towards, like if you get on one of those spinning rides and you spin towards the outer part of the seat, if you put your arm out, you can kind of support yourself and hold yourself out if you're expending a certain amount of energy to do so. And so that's kind of the idea. The electrons have these fixed amounts of energy that keep them from slamming into the nucleus. The closer they are to the nucleus, the less energy they have to expend to keep themselves out. The further they are from the nucleus, the higher the energy that the electrons have. So that's something that we've already talked about. Okay, so again, Niels Bohr planetary model, electrons exist in specific energy levels, electrons orbit the nucleus at specific distances. The electrons can jump from one energy level to another by gaining energy, absorbing energy. They can jump further from the nucleus. By losing energy, they can jump closer to the nucleus, provided there's room there. Okay, so obviously with Bohr's work, there are some things that other scientists didn't agree with, and that is, like, how is this possible? Why do the electrons have these fixed amounts of energy? Why are they in these fixed paths? Bohr's model only really described what was happening in hydrogen atoms where there's only one electron. And so another scientist came along named Louis de Broglie, and he reasoned that since we were talking about a quantum of energy or a photon of energy, a fixed amount of energy, although it's, there's a lot more to his theory than this, he was also trying to flip that description. Since energy, as we talked about, travels in waves, has frequencies, he was saying that, well, if energy can be somewhat matter-like in the fact that it has a finite defined amount, quantity that it can be in, maybe particles have an energy component in that they travel along like waves. And so his idea of matter waves is kind of grayed out a little bit. But his idea of matter waves is that particles behave with wave-like motion. And actually, if I get this off of here, we can see an example and click on this. So let's watch this little demonstration and visual animation of what a matter wave would look like.
In 1924, Louis de Broglie proposed that electrons, like light, had properties of both particles and waves. De Broglie suggested that electrons be considered waves confined to the space around an atomic nucleus. De Broglie suggested that an electron would have a characteristic wavelength equal to Planck's constant divided by the momentum of the particle. It followed that the electron waves could exist only at specific frequencies equal to energy divided by Planck's constant. These frequencies corresponded to specific energies, the quantized energies of Bohr's orbits. 3 years after de Broglie's proposal, C.J. Davison and L. Germer discovered that electrons can be diffracted by a single crystal of nickel. This important discovery provided the first experimental confirmation of de Broglie's theory.
Okay, so luckily for you, you don't have to know anything about these equations. These are these wave equations. There's some relation to the wavelength and frequency, momentum, and amount of energy that we're talking about here. But the idea is that electrons travel in these wave-like patterns. Because of that, we can actually relate that to energy. Again, that's physics beyond what we need to look at here. That was de Broglie's matter wave idea, so that particles, referring to electrons, travel in a wave-like pattern. So when we're describing how the electrons are moving around the atom, we take Bohr's idea of the quantized energy levels and apply this idea of the electrons traveling around in waves. And that's where we get closer to today's description of the atom, which is the quantum mechanical model. You may have seen it in that history of the atom worksheet described as the electron cloud model. But this is our description of the atom as we know it today. So electrons are not in fixed paths. Rather, they do have fixed amounts of energy, but they're traveling along like waves, and so that means that defining where exactly they are in the atom is a little bit not as precise of a matter as what Bohr was describing. Okay, so here are the basics of quantum mechanical model. You will be asked to compare the difference between quantum mechanical model and Bohr's model. So there's some things that are the same. So in Bohr's model, there was a nucleus, there were energy levels, and the electrons were in energy levels at fixed distances. The difference, though, is that with quantum mechanical model, instead of fixed circular orbits, electrons are traveling in waves, and as a result of that wave-like motion, we can see some other ways to describe the locations and energy levels and orbitals of the electrons. So again, in the quantum mechanical model, electrons act as both energy and matter, so that means they have mass because they're particles, but they travel in a wave-like pattern. Because of their travel patterns, we describe the electron's location as an orbital, and notice it's not the same thing as the word orbit. So orbit is what we use to describe that circular path like the planets orbit the sun. Now we're calling it an orbital, so it's along the same idea, but an extension of it. So we call an orbital a region where there's a high probability of finding an electron. And so when you think about an electron buzzing around in a wavy pattern, it's basically kind of difficult to define exactly where it is. Kind of like when you see a fan spinning and you see the blades of the fan. When it stops, you can see the individual blades, but once it's spinning around, it kind of just looks like one big blur of fan blades. That's kind of how we're picturing this electron cloud. So where I'm likely to find the electron is wherever that cloud density is the greatest. Kind of like with the fan, we can see where, we can see the fan blades, and there's like a darker region. That's where we're most likely to find the fan blades themselves. Lastly, then, an orbital can hold a maximum of 2 electrons. So again, there's going to be these regions where we're likely to find electrons. As we'll come to talk about, they've got all different shapes and sizes, and they can hold a maximum of 2 electrons apiece. So there's a picture of what one of these electron clouds might look like. So the darkest area of the cloud is where we're most likely to find the electron. Orbitals come in different shapes, but only hold 2 electrons each. And so QMM stands for quantum mechanical model, and we use this to describe where exactly the electron is, because this is going to be a fundamental thing when it comes to talking about the reactivity of atoms. Why does one element react with another one? It all comes down to these describing where the electrons are and understanding what the electrons are doing. So when we're writing orbital diagrams, electron configurations, that's what we're trying to show is where are the electrons in the atom? What type of energy level? What type of sublevel? How close to the nucleus are they? What type of region are we likely to find the electron in? Are they sharing a space or not? That's what the electron configuration can help us to identify, or that's what we're trying to describe with it. Okay, so we've got energy levels in the quantum mechanical model. These are called the principal energy levels, level 1, 2, 3, 4, 5, 6, 7. Closer to the nucleus, as you can see, the lower the energy level number is. And so these are called the principal energy levels, and they're labeled N. So you're going to see this notation. N is our symbol for the principal energy level, and it's some whole number between 1 and 7. Lower the number, the closer the energy level is to the nucleus. So we've seen that already in our worksheet D, where we have the energy levels in front of the sublevel types. So that's telling us which level. Again, that's kind of synonymous with what Bohr told us about. Then within each energy level, there are sublevels. So how we know all this comes from a scientist named Schrödinger, who took de Broglie's ideas and applied mathematical equations way beyond the scope of this course, way beyond what we are really able to understand at this level. But basically, by treating the electrons as waves, we were able to calculate or figure out that they were actually in these sublevels as well. And so here are the 4 different types of sublevels, and in each sublevel type, so as we noticed this in our worksheet D, each sublevel type has a certain number of orbitals. So if you remember, the S sublevels all had just one box, one orbital for them. And if each orbital holds 2 electrons, then that's where this number comes from. The S sublevels have spherical shapes. So again, it's a spherical region where you're likely to find the electron. We've got sublevel, the P type, holds up to 3 electrons. So we saw this also on worksheet D. And again, if each one can hold 2, that's why the P can hold up to 6 electrons. That has a dumbbell shape. I'll show you what that looks like on the next slide. Then we've got D, which has 5 orbitals. So we did not see this on worksheet D, but we should know how many orbitals it has. And again, if each orbital holds 2 electrons, then that's 10 total electrons. Has a complex shape. You don't really need to know that. And then for F, as our 4th type of sublevel, contains 7 orbitals and therefore can hold up to 14 electrons. S has the lowest energy, P is the next highest, D is next, and then F. So again, if I have an energy level, a principal energy level, and there's sublevels dividing up every single principal energy level, the lowest sublevel, lowest energy sublevel is going to be S within a principal energy level, and then P, and then D, and then F. So this is the order they're always going to come in when we look at that filling order. All right, so here's what we're talking about. So we've got our nucleus in the center. We said 1s, so the first energy level has actually only got the one sublevel, 1s, and that's why we only see that in that worksheet D when we're looking at the electron configurations and orbital diagrams. So notice the first energy level, n equals 1, only has 1 sublevel. Second energy level, n equals 2, has 2 sublevels. And that same pattern continues on. So the third energy level has up to 3 sublevels, 4th energy level 4, and so forth. The larger the orbital, the higher the energy is. So notice 1s is closest to the nucleus, that's a small sphere. 2s then is just a little bit further from the nucleus, so that means that the electrons that occupy the 2s orbital would be somewhere in this this spherical cloud, a little bit further from the nucleus than the 1s. The p orbital, so now we can see what this dumbbell shape, so like this one dumbbell, that's one p orbital, and notice how many I've got drawn here. So there's a second one, and there's a third one, and so depending on their orientation in space, we've got like the x-axis here, got the y-axis here, and the z-axis, so coming out in 3D, those are the 3p orbitals, which we saw represented with boxes in our worksheet. And notice the 2p orbitals are sticking out slightly further than 2s because they are slightly higher energy, and we said the higher the energy, the further they are going to be from the nucleus, the area where the electrons can be found. Okay, so here's the shapes represented for you. So notice here's those p orbitals. So there's 1, 2, 3 of these dumbbell shapes that make up one whole p sublevel. But again, each orbital holds 2 electrons apiece, and the 3 of them together make those that max capacity of 6 electrons that we talked about. D, when we say there's a complex shape, here's what it looks like. So there's kind of these 4, kind of looks like flowers, kind of in these 2D planes, and then we've got this other weird shapes like a donut with the dumbbell shape. And 7, the F, we don't even have a picture of. You should be able to describe that S is spherical and P is dumbbell shaped. But you should definitely know these numbers. Actually, not the lobes, just these numbers right here. Okay. So in our energy levels, so N equals 1 has one sublevel, N equals 2 has two sublevels, S and P. N equals 3 and N equals 4. We already talked about this, already mentioned it, but N equals 3 has three sublevels, S, P, and D. And again, if I add up all of these, so S can hold 2, P can hold 6, D can hold 10, so that's where I get this total of 18 from. For N equals 4, has four sublevels, so S, P, D, and F. And again, this is the order they would fill in, so 4S would get filled in first because it's lowest energy, then 4P, then 4D, then 4F. And again, if I added up all those amounts, S holds 2, P holds 6, D holds 10, F holds 14, that all adds up to 32. And we looked at this in our worksheet before, worksheet D, the Aufbau principle, but again, lowest energy levels get filled in first. This is the order, so the ones in red are the ones you're going to have to know. We've seen these at least up to 3P in our work in worksheet D, and you'll need to know up to 4S. So 1S, 2S, 2P, 3S, 3P, 4S. So those all are the order that you need to know for your test, and the rest of this order, if you need it, I'll give it to you. But again, we fill in, however many electrons the atom has. We keep filling up each lower energy level with the max capacity until we run out of electrons to distribute. When you're writing electron configurations, notice that these commas are not in there. So sometimes people mistakenly copy those down. Your electron configurations should look like they did on worksheet D. There's no commas, there's just the series of the principal energy level, the sublevel type, and then there's going to be a superscript up here telling you how many electrons are in that particular sublevel. So again, here's the order of filling. Notice that the energy of the sublevels get a little bit overlappy and a little bit complicated, so that's why you're only required to know up to 4S, because then there's some overlapping in energy, and actually 4S fills in before 3D, and so forth and so on. So again, this is the order of filling, so notice 1S, 2S, 2P, 3S, 3P, 4S, then 3D, then 4P, then 5S, then 4D, then 5P, and so forth. Other rules that we talked about, Hund's rule. So here it is down here. So maximum number of unpaired electrons will result. So this really is only something that we need to worry about when we're drawing orbital diagrams, where electrons, if they don't need to be paired up in an orbital, and again, these are equal energy orbitals, so within the same sublevel, electrons will spread out if they can. And then lastly, we've got the Pauli exclusion principle, which if we're also drawing orbital diagrams is where this is going to come up. If the two electrons are sharing an orbital together, then we need to show them with opposite spin, because we know that electrons actually will not share the same space unless they've got opposite spins. Alright, so that's where we'll stop for this, and we will be talking about writing electron configurations and drawing orbital diagrams in class.